And here's our second example of how we can use our equations of motion and graphing to solve another problem, another motion problem in one dimension. So here we have a car, and I know it doesn't look much like a car, but that's my level of drawing cars. And it starts at 0 velocity. It accelerates at 1.6 meters per second squared for 15 seconds. Question is, how far did it travel during that first 15 seconds? And I'm going to call this a 3-segment or 3-section problem, where the first segment is the initial acceleration of the car. Then the acceleration goes to 0 for 70 seconds. How far does it travel during that second segment of its motion? And then finally, during the third segment, the acceleration is negative, so it's slowing down. The final velocity is 0. How long did it take? And how far did it travel during that third segment? So let's make a graph of that. Let's make a graph of velocity versus time. That's probably our best bet. And let's see what that looks like. So here's our velocity versus time graph. Velocity in meters per second versus time in seconds. Now, notice in the first 15 seconds, it accelerates at a constant acceleration, 1.6 meters per second squared, for 15 seconds. So it will reach a certain velocity. Then it stays at that speed for the next 70 seconds. So 70, so this is 15 seconds. 70 plus 15 is 85. And then it slows down rather rapidly at minus 2.4 meters per second squared for an unknown number of seconds. All right, and so time in the third segment is equal to, so we're looking for that. And we're also looking for x in the third segment. So the subscripts tell you what segment we're in. Okay, so starting with the first segment, we accelerate at 1.6 meters per second squared for a total of 15 seconds. How fast is it traveling at the end of that? Well, I think we can do that by using this equation. V is equal to v sub naught plus a times t. That, by the way, is one of our 3 equations of kinematics. So initial velocity is 0, so we can say v when time equals 15 seconds is equal to 0 plus acceleration of 1.6 meters per second squared times the time of 15 seconds. 15 times 1.6 equals 24. So v is equal to 24 meters per second, and that's the velocity obtained after the first segment of its motion. So we can say at this point v is 24 meters per second. All right, now, how far did it travel during that time? Well, the area underneath the curve in a velocity versus time graph represents the distance traveled. So we can say that x sub 1, the distance traveled, is simply equal to the area of this little triangle here. So it would be 1/2 the base. The base is 15 seconds times the height is 24 meters per second. Like that. So 24 times 15 divided by 2 equals 180 meters. So it's 180 meters. So that's the distance traveled in that first segment. Now, the distance traveled in the second segment is pretty straightforward. It's simply the area of that second segment. So therefore, we can say that x2 is equal to the area of that second segment. This is area 2, which is equal to, since it's a rectangle, the base times the height. The base is 70 seconds, and the height is 24 meters per second. Notice that the seconds cancel out. You're left with meters. So 70 times 24 equals 1,680 meters traveled during that second section or segment of the motion. Now we're to the third segment right here. Now it's slowing down. So we need to know both the time and we need to know the distance. So what other equations do we have at our disposal? We have this equation right here. We have x is equal to x sub naught plus v sub naught t plus 1/2 a t squared. So we have this equation. And then we have the equation v squared equals v sub naught squared plus 2ax. Now notice, with this equation, we have the initial velocity, we have the final velocity, we have the acceleration. With that equation, we can actually find the time. This equation only has one unknown in it, so let's go ahead and use that for segment 3, because I don't want to be too crowded here. So the equation becomes final velocity is 0, initial velocity 24 meters per second, plus a minus 2.4 meters per second squared times the time. Time is the only unknown there. So notice I can move this over and divide by that. So we have minus 24 meters per second divided by minus 2.4 meters per second squared equals the time, and so therefore time equals 10 seconds. So using that equation, I can determine that the time here is 10 seconds, so 85 plus 10, that gives me 95 seconds for the total time travel. So time 3 here is equal to 10 seconds. And now finally, how far did we travel? Again, we can use the advantage of having a graph here. I need to find the area of that. I can say that x sub 3, the distance traveled in the third segment, is equal to the area of that segment, which is equal to 1/2, because it's a triangle. The base, which now we know to be 10 seconds, times the height of 24 meters per second. You can see that's 240 divided by 2, or 120 meters. So we travel another 120 meters during that last segment of the motion. And that's how we can use a graph very, very readily to solve problems like that, and of course in tandem with the equations of motion.